Okay, folks, we're going to do something really fun now. We're going to take something that you are really familiar with, hybridization, and we're going to add a lovely Chem twist to it. So we're going to discuss the hybridization of atomic orbitals to form sp3, sp2, and sp hybrid molecular orbitals. Let's go for it. So I just want to describe just a little bit of the first attempts to do this. So in a first attempt to try and make molecules out of atomic orbitals, if we think about something like H2O and this notion that we can create overlap in these internuclear zones, if we try to do this just directly using 1s orbitals for hydrogen and 2p orbitals for oxygen, right? We can see the 2p orbital shape for oxygen and the 1s orbital shape for hydrogen. We would predict the bond angle in water to be 90 degrees, which we know that that's not the case. It's not consistent with observations. So clearly something else is going on. And so valence bond theory is an attempt to describe that. So we first have to talk about this idea of promotion. So this is the excitation of electrons to higher energy orbitals with a presumed benefit of eventual energy lowering. This is different than just normal like excitation like we talked about in atomic spectroscopy. The idea here is that there will be an eventual benefit of energy lowering to do the promotion in the first place. Hybridization is the combination of atomic orbitals to create a new set of orbitals capable of describing bonding in simple molecules. And then we rely on what's called the VSEPR, the valence shell electron pair repulsion model, to come up with the best possible approximation. And that best possible approximation is based on the idea that electrons will repel each other, so they want to spread out as much as they can. So in this case of oxygen making this 90-degree bond angle, we know that it can make a larger bond angle. It can spread out a bit. So something a little bit more complicated is going on than just simply combining s orbitals and p orbitals. So this first idea, so we'll use carbon. So carbon is the basis to describe hybridization. And if we look at the atomic configuration of carbon, it's a 2s2, 2p2. And we rely on this idea that there's an open position right here, and that we could promote one of our paired electrons into that open position with this eventual idea that there will be overall energy lowering. So now once this electron has been promoted, we have 4 unpaired electrons primed to be bonded with other atoms. And if we recognize that these 4 electrons are now going to end up being this constructive and destructive interference known as hybridization, then we get this unique set of orbitals called sp3. So the idea here is now we're going to add together just a linear combination of s orbitals and p orbitals to make this sp3 shape. So this I expect you probably remember from your Gen Chem and your OChem. What you're probably not familiar with is how it all shakes out. So the way that we do that is by making all of the necessary plus minus combinations that we can do with 2s, 2px, 2py, and 2pz orbitals. So for example, our first linear combination is all plus states. And so if we might imagine, if we're drawing this in a 3D coordinate system, and hopefully I can give this some justice here, then when we have all of these as positive, we can imagine them functioning like a unit vector, all in the positive coordinate space. So that's going to end up looking, something like this where this vector, I'll call that H1, that's going out all into the positive Z, positive X, and positive Y. So now you can see here, we apply our linear algebra and make all of the necessary plus minus combinations. So for H2, we keep things in the positive Z, but now we make them in the negative X and the negative Y. So I think I can draw that. That will look, something like this, H2. Let me make that 2 just a little bit more clear. Dose, there we go. So then now H3, we alternate the positive negatives once again. So we stay in the negative X, this time the positive Y. Now we're in the negative Z. So that will end up, looking something like that out there. H3, I know my drawings are terrible here. And H4 will now have that in the positive X, but the negative Y and the negative Z, and that will end up looking something like this, okay? And, right, that looks awful, apologies. So a better way to draw that might be something like this, right, where I have 2 going this way, I have 1 coming out at me, and I have 1 going into the plane of the board, right? And hopefully we're familiar with that shape. That gives us our tetrahedral shape with our 109.5 degree bonding angle. So now you can see I've got something really neat over here. I've got this all coded up in Mathematica, which we'll do. I have my full basis set for the sp3, and each one of these functions is the proper atomic orbital for that respective label. And now when I plot this all, you can see I get 4 new orbitals. So there are 4 there. The red describes the positive region. The green describes the negative region. And you can see it looks very much like our tetrahedral molecule, which is pretty cool. So if we keep going down the line and just kind of trying to figure out where this positive and negative interference comes from. So this is our radial profile for the 2s orbital, right? 2 for n and 0 for L. And this is our radial profile for p, the 2p orbital. And so when we look at those, I know this is like a weird drawing here. So the 2s is labeled in the blue. There it is. And it's giving us that same kind of idea we saw before, where in the positive radii and the negative radii, it looks identical because the s orbital is positive all around. But now if we look at the 2p radial function given by yellow, it's going to have, in this case, the way this picture is drawn, the negative region is up here and the positive region is up here, right? So you can see that positive region is given right there, and then it flips signs right there. So all the same, what we end up with is a region where there's predominantly constructive interference, giving us this like larger lobe shape, and this region where there's destructive interference, giving us that smaller lobed shape. And that's what we can see on my picture right here, right? That green area is where there was destructive interference. The red area is where there's constructive interference. And there we go. You can see that famous 109.5 bonding angle. So now how do we make a molecule out of this? Well, we had empty orbitals, right? We had electrons in each one of those sp3 orbitals. Now we can make a singlet state out of those by overlapping a neighboring hydrogen 1s. And you can see in that region where there's mutual overlap, bonds will accumulate and form. Specifically, now that would make a sigma bond. So we would have 4 sigma bonds all around in this molecule, methane. Okay, so that's all good. Hopefully that makes good sense, and that's good review from your previous coursework. Let's quickly now describe what happens with the sp2 and sp. So if I keep using carbon as my example now to describe sp2, we have, once again, this same notion of promotion. And recall in the sp3 case, we had 4 unpaired electrons, and we could pair those up to make an sp3. Well, there's another possibility behind that. And that possibility is to only use 3 of those electrons to make hybrid orbitals, and 1 remains in its unhybridized p orbital. So again, we could make 4 sp3 bonds, or we could make 3 sp2 bonds and keep 1 p orbital. So now our basis set for this becomes the following. We only have 3 electrons, so we get 3 basis sets. And now similarly in our x, y, z space, we're going to have a similar procedure where we now look at different combinations, in this case of the px and the py. So we are going to make this unhybridized one specific to the pz. Now this gets really difficult for me to draw, but all the same, you might notice that there's no pz combinations. So we're going to end up with stuff that looks like the following. We're going to see, and I didn't do this very well because that one's like square on the y-axis, right? So we'll just kind of approximate it. H1, H2, H3. That doesn't look very good, so let's go to the Mathematica to get a better description of that. So here's my basis set, and what I want to point out is if I orient this in the same way that I've got this picture drawn, you can see it makes a planar configuration, right? We only have stuff going on in the x and the y. So our unhybridized p orbital is up here in the z-axis. So I'll note here that we keep that. Let's see if I can draw that in a different color. So our pz orbital remains up here, whereas now we've got our hybrid orbitals going out in this way. Okay. All right, let's get a better picture. I've got one on the next slide. So here is a much better picture. So we can see there's my planar sp2 configuration, and with my unhybridized p orbital. And this allows for some very interesting bonding patterns to happen. And we can use the molecule ethene as a good example to describe that. So here we have our sp2 carbon in the middle. We can see that it had 1 electron in each of those sp2 orbitals, and a singlet state can be made with a neighboring overlapping electron. In this case, hydrogen overlaps over here, so we make 2 sigma bonds right there. I guess we'll keep the blue color, that's fine. So we get sigma bonds here, and of course there's an identical carbon over there, so we get other sigma bonds. Now we have 1 electron available from each carbon in the sp2. That makes another sigma bond from their mutual overlap. And then interestingly, in the same thing that happened in our description of the pi orbital, we have an empty electron in each of these unhybridized pz AOs, and now those can combine to form a singlet state to make a pi bond that we can see right here. And of course, this will have a planar structure in the sp2 region, and the pi bond will be above that internuclear zone. So let's move on to our next case, and we'll just finish this off very briefly. So now we can still see the possibility of promoting to create 4 unpaired electrons. But now with those 4 unpaired electrons, we could hybridize 2 of them and leave 2 of them and their respective atomic orbitals. And in that case, because we only have 2 combinations here, our basis set is much less complicated. And you can see we get this lovely linear shape. Okay. where now this is specific to the z-axis. And of course, we can now use this to describe an even more complicated molecule like acetylene, where we have only one electron in each of our sp orbitals, right? There they are. So we can overlap a hydrogen with these outer ones, right, to make a sigma bond and a sigma bond. We can overlap our two carbons, the carbon-carbon sp, to make another sigma bond. But now recall, because we had an electron in, let's say, the px and the py, it's arbitrary which I selected, right? That's going to allow us to make 2 pi bonds. And I kind of like to describe it as this like barrel of electron density. So as we might imagine, that's why these triple bonds are quite strong, because not only are the nuclei being held together in their internuclear zone, they're also being held together outside of that area. That's it. That's about it for valence bond theory. We're not going to really spend too much more time with this. And we are going to dive deep into this exercise, getting these things all plotted out, which should be pretty fun. Okay, I'll see you in the next video.